After two fairly long sessions, hopefully this one will be a bit quicker. Right? Now, earlier we had a language of this form. Before we had regular TM. X here was regular TM, and is of this form, where X is a regular language. We can create similar undecidability proofs for where X might be a context-free language. Okay, so you might have like context-free TM. And this is the language, and the corresponding problem then would be, can you find a Turing machine that has a given language, whose language has a certain property, like the language of that machine is I don't know, a context-free language, or a decidable language, or a finite language. In other words, an X language. Okay, so here are three more undecidable languages that we could prove in similar ways. Like, your X here might be context-free, it might be decidable, it might be finite, and so on. Okay? In fact, this makes us suspicious that for any property P about the language, you'll get an undecidability proof. And it's called, there's a more general result than these particular cases, called Rice's theorem. It's a rather famous theorem in theory of computation. So here's the statement. So testing any property of the languages that a Turing machine can recognize, that is finding a Turing machine that can decide that whether a particular Turing machine, whether a particular Turing machine's language has a certain property. There's no Turing machine that can answer that, right? And that's the computational problem. And the equivalent language problem is, it's true for whatever X is. X is some property of this language. Okay, X is some property of this language. And Rice's theorem says, when you translate it that way, whatever property P you put here, this language has some property P, then that language, undecidable. Now that's pretty powerful stuff if you think about it. Right? So it's not surprising that Rice's theorem, R-I-C-E, Rice, it's a word I don't like very much, you can imagine, as a Westerner living in China. Too much rice, every damn day, rice. I have a Chinese wife, right? To her it's unconscious, it's like a fish in water, it's like Asians and rice. I just grew up in this stuff. Okay, rice, so Rice's theorem. Okay, now a rewording of what Rice's theorem states. So the problem of testing whether some Turing machine's language, L of M, has some property P, that problem is unsolvable. Right? I'll say it in words. You're given some random Turing machine M. Okay. You find its language, so L of M, and you're asked, does that language, L of M, does it have some property P? Like it might be context-free language, or a regular language, or a decidable language, or whatever, some property P. Can you find a Turing machine that will answer yes or no? Does that Turing machine... We're talking about two different Turing machines again. Okay. We have some random Turing machine M1. Okay. and it'll have its language. So L of M1. And you're asking whether there's some other Turing machine called M2. Can that machine M2 decide whether the Turing machine M1's language, so L of M1, whether that language has a certain property, P? No. There is no such machine M2. And put in language form, the language would be undecidable. Okay? Language will be something like this. You could put like, I don't know, like PTN, right? P for property. So all this will be the same, and LM has the property P. Okay, that'd be Rice's theorem, effectively. Okay, now, in fact, Rice's theorem is one of the exercises at the end of the chapter. So maybe when I get round to doing problem solving, I have a backlog, should do that, because Rice's theorem is really important. Okay, so move on a bit, new topic, somewhat, new idea. I mentioned it in the first session, and that is we don't always have to use the language ATM to help us prove that some other language is undecidable. In fact, we're going to use ETM, the one we just proved before. Now that we've proved it, we can use that in a reduction type proof to show some other language is undecidable. Right? And sometimes it's easier. Okay? Right, so let the problem be, we're given two random arbitrary Turing machines, M1 and M2, and the question is, the computational problem is, are these two machines equivalent? Okay? In other words, do they do the same job? Do they both decide or recognize? I'm not quite sure what they mean by equivalent. Well, let's say, do these two machines, two Turing machines, M1 and M2, do they both recognize the same language? I guess. Right. Now, so in other words, can you find a third Turing machine, M3? Is there a Turing machine, M3, we'll label it, that can decide whether, when it has as input the encoded descriptions of two Turing machines, M1 and M2, so it would be angular brackets M1, comma M2, okay, so that encoded description of two Turing machines goes into machine M3, and then M3 has to decide whether those two Turing machines, M1 and M2, are equivalent or not. There is no such machine, M3. Right? And if you translate that computational problem into a language problem, then that language would be undecidable, and the computational problem would then be unsolvable. Now, for this particular problem, the equivalence problem, if you like, between two Turing machines, now you could prove the language equivalent problem to be undecidable using ATM. That can be done, but just to make the point that you don't have to stick with that one all the time. You can use other languages that have been proven to be undecidable. Okay, so we're going to use this one.